And now we're going to talk about equilibrium. This section of the course is called Equilibrium Thermodynamics. And we talked a little bit about equilibrium at the very beginning of this section, but now we're going to look at it in a little more detail now that we know about things like free energy and chemical potential. So these first three we talked about before at the very beginning of the course, and here's another one we're going to add. Let's first review these three things here. System no longer evolves with time, or if you're looking at a chemical reaction, no product is formed or no reactant is used up in a chemical reaction when the reaction is at equilibrium. So just to review what we mean by this, what we're going to measure is, let's take simple reaction A, which is in equilibrium with B. And over here we'll measure the concentration of A or the concentration of B as a function of time. So we can do this, measure these concentrations spectrophotometrically or something like that. And let's say at time equals 0, at the start of the reaction, the concentration of A is some concentration, say A0, and the concentration of B, say, is 0 at time equals 0. All right, so this concentration is A0, and initially this is 0. So as the reaction goes on, A is converted into B, so the concentration of A decreases, but then it levels off, like that. The concentration of B, initially at 0, then increases like this, and then it levels off. So the region here where there's no change in concentration in a chemical reaction, this says this would be at equilibrium. And these lines should just be straight, they're not changing at all. Okay, so that's what we mean by system no longer evolves with time with the specific case for a chemical reaction. Let's look at energy. Energy is at a minimum, and we said from introductory chemistry, the energy we're interested in at constant temperature and pressure is the Gibbs free energy G, and this will define more clearly later, but let's just call this the extent of the reaction. Okay, so over here you have lots of products, over here you have lots of reactants. So at various places along the chemical reaction, you can measure the Gibbs free energy G, and what you find is that there's a place where the Gibbs free energy is minimum, and at that point, at that extent of the reaction, where you have a certain amount of reactants and products, you're at equilibrium. There are no gradients in intensive variables, and therefore no fluxes of corresponding extensive variables. We talked about this a little bit. Let's take, say, the extensive variable electric potential. For instance, if you have a battery, and you hook this up with a wire, electrons will flow. That's the extensive variable that's associated with the electric potential that you have in the battery. Electrons will flow from a high region of electric potential to a low. So for example, when you're not at equilibrium, if you look at the electric potential, we'll use a simple psi, and this is some spatial coordinate, some region of space, and over here you have a high electric potential, and down here you have a low electric potential. Electrons will flow in a region of space where their electric potential is large, like over here, and they'll flow down to a region where their electric potential is low, like over there. If the system is at equilibrium, the plotted potential versus some spatial coordinate will be flat. So now nothing's happening. If you have an electron right here, there's no potential gradient. Potential gradient is related to force. So there's no force to move these electrons from one place to another. So the system now is equilibrium. When there's no gradients in an intensive variable, and therefore no fluxes of the corresponding extensive variable. And now finally, given our criteria of spontaneity that we talked about 2 lectures ago, we said that a criterion of entropy is, or criterion of spontaneity, is that entropy increases. So spontaneous ds of the universe or isolated system is greater than 0. So things will keep happening until this criterion is no longer met. So let's just see. Let's look at, here's entropy, and here, well, I don't know, what do you want to put here? Time, perhaps. So the entropy will go up and then reach a maximum. So right here, you're at equilibrium. And here, ds is equal to 0. ds is slope. The slope is equal to 0. So there's no spontaneous change. The system is at rest, equilibrium, no reason for it to change. So it's just hanging out here at equilibrium, hanging out here at equilibrium. Okay, so maybe we have a little better understanding of chemical equilibrium in general and chemical equilibrium. Actually, let's go back here and look at the entropy for a chemical reaction. So here you have S, and here you have extent, defined a little later in this lecture. All right, so you'll have something that increases in entropy, and then you'll reach a maximum, and then if you go over to the other side where you have lots of products, the entropy will start to decrease again. So right up here at the top for a chemical reaction, here we have equilibrium, where the entropy has reached a maximum. Okay, well, what else can we say? What does chemical equilibrium mean? Well, from introductory chemistry, you sort of know that the reaction proceeds neither to the left nor the right net, and the extent of the reaction, there's that extent of the reaction, doesn't change. So sorry, this should be dc is equal to 0, where the symbol here, Greek letter xi, I think it's xi, is the extent of the reaction. We'll get into that in just a second. Also recall from introductory chemistry that the equilibrium, even though the concentrations are not changing with time at equilibrium, so here we are at equilibrium, the concentrations of A and B are not changing. Nonetheless, this reaction is still occurring. Even at equilibrium, A is converted into B and B is converted into A. Just at equilibrium, the rates of the reactions forward and reverse are the same, so you have no net change in A or B. But still remember that A is converted to B and B is converted to A at equilibrium, and that's what's known as dynamic equilibrium. Also, we know at constant temperature and pressure, dG, from a previous lecture, dG equals 0 at equilibrium. That's what we said here. So dG is a slope, so dG is equal to 0 at equilibrium. Okay. And then we'll get into this in just a second. All right, let's look in more detail what extent of reaction means. All right, let me define what I mean by extent of reaction, given this symbol C. And this, of course, will be a function of time, because as time goes on, the reaction will be more or less toward the beginning. So let's define this as the number of moles of some reactant species I. So this will be will right now identify this with some reactant or product species, but we'll find later on we don't need that I, minus the number of moles of that species at time equals 0, divided by this symbol nu I, where this is the signed stoichiometric. I knew I was a chemist when I could spell stoichiometric, signed stoichiometric coefficient in the balanced chemical reaction. What I mean by signed means negative for reactants and positive for products. So for example, if we have 2A goes to B, say, just make it interesting, 3B. The signed stoichiometric coefficient for A would be -2, minus because A is a reactant, and the signed stoichiometric coefficient for B is +3. So that's what that means. So note that at C, for some species at time equals 0, this means the number of moles is the number of moles at time equals 0 is 0. So the extended reaction starts at 0, and then eventually when it reaches equilibrium you'll have a certain number of moles here, and that will be subtracted off from the moles that you started with and then divided by the signed stoichiometric coefficient. Then you get a number which will be in moles. So C is in moles. Let's take an example. Let's take A, say goes to 2B, and let's make this at equilibrium. Might as well. This could be at equilibrium too. All right, so and also say at time is equal to 0, we have 2 moles of A and 1 mole of B. Okay, so as we said, at time equals 0, the extended reaction will be 0. You're just subtracting 2 minus 2 for A and 1 minus 1 for B. So let's say at time is equal to 1 minute, A now is, let's make it more interesting. Let's make this 1.5. And B now is equal to, you started with 1 mole, but for each mole of A, you now produce 2 moles of B. Or if you lost a half a mole of A, you produced 1 mole of B. So the amount of B at time equal 1 minute is what you started with plus what you produced from this reaction. So the total amount is 2 mole. All right, so let's look at the extent of the reaction at time equal 1 minute. All right, so the extent of the reaction for A at time equal 1 minute will be the number of moles of A at 1 minute, which is 1.5 mole, minus the number of moles we started with, which was 2 mole, and we're divided by the signed stoichiometric coefficient. The signed stoichiometric coefficient is -1, minus because it's a reactant, A is a reactant. So -1. So this comes out to be 0.5, positive 0.5 mole. Now let's look at the extent of the reaction for B at time is equal to 1 minute. That's equal to how much B was present at time equal 1 minute, which was 2 mole, minus the amount we started with, which was 1 mole, and the signed stoichiometric coefficient, A goes to 2B, is just 2. So this is 0.5 mole. In fact, if you just extrapolate this, no matter which reactant or product you choose for an arbitrary chemical reaction, as long as you're dividing by the sign stoichiometric coefficient, you're going to get the same extent of reaction. If you measure A, you measure B, or if you have a more complicated reaction, measure C. No matter what reactant or what product you measure at some particular time, you're going to get the same extent of reaction. So that's why these subscripts here are not needed. So the extent of reaction does not depend on what reactant or product you choose because of the way it's defined, and that minus sign will take care of disappearance of reactants. All right, so we say in general, we can say C will be defined as the number of moles at some time t minus the number of moles at some time t equals 0 when you're starting it, divided by the sign stoichiometric coefficient. This still have to be a subscript here because you're measuring a particular reactant, but you'll get the same extent of reactant. And we'll find it useful later on to find out, to look at the derivative of C at some time, and I'll denote these subscripts. I'll put time equals 0. I'll denote. All right, fine. I'll keep them. All right, so again, the extent of the reaction is measured at some particular time. Okay, so that how the extent of the reaction changes as some function of time, which is independent of what you're measuring. That would be how this thing changed. So d n sub I, that species of time, doesn't matter whether it's reactant or product, minus n sub I at time equals 0, as long as you divide by the sign stoichiometric coefficient, which is a constant. N sub I time equals 0 is also a constant, so this is just equal to 1 over nu sub I constant d n sub I of time. Okay, so both of these are time dependent. Or in other words, how the number of moles change at some particular time in the reaction is the sign stoichiometric coefficient times how the extent of the reaction changes. And this no longer has to be, this does not depend on what you measure. So that's kind of handy. We'll find that later on, that the extent of the reaction will be one single number, which will be independent of what we're actually measuring. Okay, so that's what we mean by extent of reaction. Now let's look at these two equations and see what we can glean from them. Okay. Now, as we said, at equilibrium, dg is equal to 0, so g is not changing. We also said in the previous lecture that dg at constant temperature and pressure, dg will be the sum over all reactants and products of the chemical potential of that particular reactant product times how the number of moles of that reactant product changes. That is equal to 0 at equilibrium. Okay, let's make this handy substitution here. Okay, so now we can get rid of the dependence of this variable here that's changing with just a single one, so we don't have to worry about C. So this is just equal to the sum of mu sub I, nu sub I, sine coefficient dc. And that is equal to 0 at equilibrium. Now let's consider just a simple chemical reaction, A, in equilibrium with B. Let's write this down, this equation down for those. So we'll have the chemical, the stoichiometric sign, stoichiometric coefficient here will be -1. So this will be minus mu sub I dc. And then, so we did, this is a sum over the reactants and products. We have one reactant. We did that one. Let's do the product B. The sign coefficient is 1, so that's +1. Mu, sorry, I should put here A, mu B times dc, and that's equal to 0. Or in other words, since we have this extended reaction doesn't depend on A or B, we can say that minus the chemical potential of A plus the chemical potential of B is equal to 0 at equilibrium. Or in other words, at equilibrium for this A goes to B reaction, the chemical potential of A is equal to the chemical potential of B. All right, so that's an interesting finding. Let's see, is that what we said here? Well, yeah, so we're sort of going here. I'm not quite sure what this means. Equilibrium single component. Well, I guess that just means you just have one component, not A goes to B, but in fact just A. The chemical potential at equilibrium of that one component would be 0. Okay, so what have we done here? Well, we've advanced our understanding. We've said now that at equilibrium, for that A goes to B, the chemical potential of the reactant is equal to the chemical potential of the product. In other words, what you're doing, you're starting out the reaction, the chemical potential reactants or products are not equal, they're out of balance. So the system is going to rearrange so that you're going to have chemical potential balance. So the reactants, the chemical potential of the reactants is going to equal the chemical potential of the products. And we showed that case for a specific case, A goes to B. All right, there's another thing we could sort of extract out of these ideas we just presented. We said that GG is equal to the sum of the sign stoichiometric coefficient. Here we're summing over products and reactants. The sign stoichiometric coefficient of the product to reactant times the chemical potential times dc. Let's see how D changes, or sorry, how G, the free energy, changes with extended reaction. And this we're going to define as delta G of the reaction. That's the delta G that we learned about in introductory chemistry. That's equal to just the sum of the sign stoichiometric coefficient times the chemical potential of that particular species. C, remember, doesn't depend on whether you measure reactant or product, so we just pull that over there as a constant. Okay, so, and as we said, as we said, that's what we have here at equilibrium. So that's equal to 0 at equilibrium. In other words, if we look at G, and now we're actually we know what we're talking about when we put down here extended reaction. We have something like this, reaches a minimum and goes up this way. So right there is at equilibrium. And how G changes with the extended reaction is equal to 0 right there. That the slope of this is 0 right there at the minimum. And furthermore, we said here, this is, we're going to call this delta G of the reaction. So the slope of, and of course delta G of the reaction will depend upon where you are. If you start right here at equilibrium, delta G of the reaction will be 0. But if you're up here, delta G of the reaction will be greater than down here. So the slope of that plot is equal to delta G of the reaction. That's because we're just defining it that way. All right, so keep that in mind. Okay, now let's go on to the next slide. This is non-ideal, and also I should probably say non-standard conditions. Okay, so let's look at these equations, see what they come from. And down here is where we're talking about non-ideal behavior. Let's first talk about this. Next page. All right, so let's first start by realizing that G is a function of temperature, pressure, and number of moles. It's a function of pressure at constant T and number of moles. So now we're going to say, how does G change with pressure? Well, that's how G changes with pressure at constant temperature, number of moles, times dP. And, let's make the assumption this is an ideal gas. No, actually we don't. You don't have to make the assumption it's ideal gas. Remember from, two lectures ago perhaps, that this is volume. How G changes the pressure, constant T, is volume. Okay, so we can write this as V dP. Okay, so let's integrate this. Let's integrate this from, say, G1 to G2 dG. This will be the integral from pressure 1 to pressure 2 of V dP. Let's make the usual assumption we have an ideal gas. So we can replace V with nRT. So this will be the integral from P1 to P2. V is nRT over pressure dP, and this we know by now is just integral, so we have delta G, G2 minus G1, is equal to nRT times the natural log of the final pressure over the initial pressure, where the final pressure is, just let's be explicit, this is G2 minus G1. So final pressure corresponds to G2, initial pressure corresponds to G1. All right, now we're going to introduce the concept of standard state. So standard state, we're going to associate G1 with a standard state. We'll give that G with a 0 up there. That means standard state. And we're going to use, and P1 then will be the pressure at the standard state. All right, pressure and standard state in Pchem, the standard state pressure is 1 bar, which is close to 1 atmosphere, but not quite equal to it. What does this mean? This means we're going to measure free energies relative to some standard state. So we're always going to have a reference for a standard state. Okay, so let's just rewrite that in the new notation. Delta G, measured from some standard state, is equal to, well, let's just be more explicit. So G2 minus G0, that's equal to nRT times the natural log of P2 over P0. And note that's 2 there, so we really don't need to carry around that 2. But, well, we can if we want. Now let's just get rid of it. So G will automatically be 2. G minus G0 is nRT times the natural log of P2 over, I'm sorry, we're getting rid of the P. Getting rid of the 2 on the P. So over P0, where that's the standard. Furthermore, we know that mu we defined was how G changes with N at constant temperature and pressure. So if we take the derivative of this with respect to n, we have how G changes with n minus how G0 changes with n, and that's equal to derivative that the n will go away. This is just RT times the natural log of P over P0. Let's call this G, we'll call this mu, the chemical potential, and we'll call this mu0, the chemical potential in the standard state, which we defined was 1 bar for gases. Okay, so if we combine these, there we go, G minus G0, or let's rewrite this as G is equal to G0 plus nRT, natural log of P2 over P0. And we write this as mu is equal to mu0 plus RT, the n goes away, natural log of pressure. Don't need to carry the 2 around anymore. Divided by P0. Okay, so that's where these two equations come from. It's for ideal gases, and we said that well, we just used this handy-dandy equation here. That came in handy. See, we learned that a while back as coming in handy. We integrated that, and we found that free energy depends logarithmically on pressure, as does chemical potential. Now, that's for ideal gases. What happens if you have a non-ideal gas? Okay, well, what you do is replace the pressure with something known as fugacity. That's a weird name, fugacity. And fugacity is defined as the pressure times the fugacity coefficient, which you can sort of think of as a fudge factor. So what these, this is the symbol phi. What phi does is correct the pressure so that you can use fugacity in here. So it's as if you're using the ideal gas equation, but you're using it with a correction factor to take into account the gas is non-ideal. This sort of corrects it back up to what it would be if it were ideal, and you can use ideal gas equation. All right, so when you replace pressure with fugacity, that's an F there, that's an F there. This you can maybe calculate, but more generally it's measured experimentally. And fugacity would be a function of pressure and temperature. And to show that the fugacity coefficient depends upon the gas, once upon a midnight weary, while I was pondering weak and weary over many a quaint and forgotten book of lore, I found this article, Fugacity Coefficients for Hydrogen Gas. And this is the American Journal of Science way back in 1964. And here's some data. There it is. Fugacity coefficients for hydrogen gas, as a function of pressure and various temperatures here. Temperature, this is in degrees C, and this is in atmosphere. What we see is a fugacity, well, this is for atmosphere, and the ones in italics are for pressure in bar. And what we see is the fugacity coefficient varies depending on what pressure you have and what temperature you have. And for hydrogen, under these conditions, the fugacity coefficients are greater than 1. Look at all that data. Cool. Okay, so they're all greater than 1. That's kind of cool. So what we've shown here, fugacity coefficients, you determine those experimentally. You multiply those by the pressure of the gas, the actual pressure of the gas, and then you get a fugacity, which you then plug into these in place of the ideal gas pressure. You plug in the fugacity. All right, well, just actually, let's sort of do that here. So we said the fugacity F was some fudge factor called the fugacity coefficient times pressure. Now for an ideal gas, of course the fugacity coefficient will just be equal to 1, so that the pressure you plug in, or the fugacity you plug into those equations here, will just be the actual pressure you measure the gas. But for hydrogen and a lot of other gases, for H2, etc., the fugacity coefficient is greater than 1. What does that mean? Well, the pressure for an ideal gas, you're going to have to multiply that by a number greater than 1. It is as if these real gases don't have enough oomph, and you got to multiply by a number greater than 1 to give enough oomph in order to put it into the those equations we just had. All right, so that's what that means. That's how you take into account non-ideal. Typically you put in a fudge factor, and when we talk about solutions, the fudge factor will be called the activity coefficient. Here it's called the fugacity coefficient. Okay, now remember from introductory chemistry, we defined something called the reaction quotient, Q, and Q was essentially the equilibrium constant, except that you weren't using equilibrium concentrations, you were using the concentrations at some particular time. Go away. This capital pi means products, so you, this means take the product of the products. Oh, weird. So this means take the first product, the second product, the third product, you multiply them together. It's like the sum, the sigma, capital Greek letter sigma, meaning sum. This is capital Greek letter pi, meaning product. So anyway, maybe you want to refresh your memory, or maybe you remember that. So what we're going to do here is to get a bigger understanding, or better understanding, a bigger understanding of what the reaction quotient means. Let's take a simple reaction. We'll do a gas phase reaction. A, that's the stoichiometric coefficient. This will be in the gas phase. Will be in equilibrium with B, stoichiometric coefficient B times molecule B, again in the gas phase. Let's look at, say, the free energy change for this reaction. Well, from our previous discussion, this would just be the stoichiometric coefficient of B times the chemical potential of B, number of moles of B times the chemical potential of B, minus the number of moles of A times the chemical potential of A. Okay, that's what delta G of a reaction will be. We also know that from our previous discussion, mu A, the chemical potential of A, will be the chemical potential of A at some standard state, and since this is a gas phase reaction, the conventional standard state will be 1 bar plus RT times the natural log of the pressure of gas A. Let's assume ideal, so we don't have to worry about fugacity and fugacity coefficients. We can write a similar equation for mu B. That will be equal to the standard chemical potential. That'd be the chemical potential 1 bar plus RT times the natural log of the pressure of B, assuming I get ideal, over this reference pressure. Note that this pressure here, at 0, corresponds to that. And by specifying a reference pressure, usually it's units of 1, you specify the units of the pressure you actually measured. So for example, if P0 is 1 bar, that means that the pressures you measure of A and B have to be in units of bar, because you want the units to cancel out, because you have to take the logarithm of something that does not have any units. So by specifying the standard state pressure of 1 bar, we are specifying what units we have to measure pressure in. That's a concept that was sort of introduced in Intro Chem. Remember, you said, well, we'll plug this into the equilibrium constant, but the concentrations will be, solution concentrations will be 1 molar, and the pressures will be 1 atmosphere. What that corresponds is that the standard state is 1 molar for solution. Standard state is 1 atmosphere. So just remember that. Okay, that's just an aside. So now we're going to use the delta G for the reaction using this. This will be B times the chemical potential of A, B times the chemical potential of B. There it is. So I'll just write that here. Plus RT times, this is a gas phase reaction, so pressure of B over pressure, standard state pressure, so the pressure of B has to be in a bar minus A. Okay, A times the chemical potential of A. That's the standard state chemical potential of A, the chemical potential at 1 bar, plus RT times the natural log of PA, the actual pressure of A, which is the viscosity because we have an ideal gas. Let's rearrange this equation a little bit. Let's call this B times chemical potential of A minus A times the standard state chemical potential of A. So I took that term and that term, put them over there. And then this will be B RT natural log of PB over P0 minus A RT times the natural log of PA over PA0. Okay, so let's continue on here. Let's call, say, B mu A0 minus A mu, B mu A0. Let's define this as delta G0, the standard state free energy change. Let's remember, this is the general equation for free energy changes. So if we just put a 0 there, 0 there, we'll put a 0 there. So there it is. Yeah. Okay. So that's the free energy change when the compounds are in the standard state. And we have like B RT natural log of the pressure of B divided by the standard state pressure. We can rewrite that as RT times the natural log of the pressure of B over the pressure of standard state pressure raised to the A power. Raised to the B power. Okay, make that a little clear there. And we can write the same thing. Say we have A RT natural log of pressure of A over pressure, standard state pressure. That'll be just RT, natural log of the pressure of A over the standard state pressure raised to the A power. This was raised to the B power. So putting all those together, these manipulations here, and using that symbol delta G to represent that, what we end up with, okay, so we're going to rewrite this equation. We made a different symbol there. We put the B up there, put the A up there, and that power. So what we end up with is delta G for the reaction is delta G0. Well, all right, we'll just put this. A plus RT natural log of PB over P0 raised to the B power minus RT natural log of pressure of A over the standard state pressure raised to the A power. And note that minus there, you just flip these around. So this can be written as delta G0 plus RT times the natural log of PB over P0 raised to the B power over pressure of A divided by the standard state pressure raised to the A power. Oh, look at that. This is kind of cool. This is, as we defined it in Intro Chem, Q. It's the, in this case, gas phase, the pressures raised to the stoichiometric coefficient of the products. This is the products. And here's the pressure raised to the stoichiometric coefficient of the reactants. And that ratio is Q. what is different from introductory chemistry is now we're dividing these pressures by the standard state pressure, so that this whole thing will be unitless when you take the logarithm. We have to take a logarithm of a number rather than something that has units. But see, that it used to be we just sort of threw that out there, and in intro chem we didn't put P0 there, we just said standard state blah blah blah. Now we know explicitly where that standard state comes from. It comes from, well, we're just defining a standard state. And we're measuring all chemical potentials and all free energies from that standard state. In this case, that. All right, so just sort of combine everything. So delta G, the reaction, is delta G0 plus RT times the natural log of Q. So there we go. That's something you're just throwing out there in intro chem. Now we know a little bit more about that. And here is the more general case where you have more than one reactant and more than one product. You just multiply them together. Okay, well, making good progress. So now let's look at equilibrium. Now that we know what Q and K are, or well, we actually don't know what K is, but let me define at equilibrium, K will be defined as Q. So this Q is at equilibrium. So at equilibrium also, delta G is equal to 0. Remember, you have a minimum free energy, so it's not changing. The derivative, the slope is 0. So this means that 0 is delta G0 plus RT times the natural log. We're going to make this switch in symbol from Q to K. Or, in other words, delta G0 is minus RT times the natural log of K. And delta G0 would be the free energy change when you start with reactants and products in their standard state and let them react. Okay, that's kind of cool. Well, that ends it for this first part of the lecture, and we'll continue on in a little while to the second part of the lecture.